Eu vou te apresentar e aí você fica à vontade, tá bom?
Beleza.
So our last speaker of this day is André Duarte, and he's going to talk about minimal idempotents in twisted group algebras of cyclic groups. So André, please.
Good afternoon, everyone. First of all, I want to say thanks to all the organizers. I'm really honored to be here today. So thank you for having me here. What I present today. Oops. So I present these three topics: idempotents, codes as ideals, and our main topic is this number 3. So minimal idempotents in twisted group algebras of cyclic groups. So let's get started with idempotents. So remember that in element E in the ring R with identity is called an idempotent if the square of E is equal to E. And if R is a semi-simple ring, then we have two well-known facts. The first fact is that every ideal is generated by an idempotent. And second, every idempotent is a sum of minimal idempotents. And remember that minimal idempotents are idempotents which generate minimal ideals. So in order to obtain all ideals in semi-simple ring, it is important to know all minimal idempotents. Okay, but what the theory of idempotents has to do with coding theory, for example? Let us present some facts. The first fact is about cyclic codes. And cyclic codes is a well-known family of codes which were introduced by Eugene Prank in 1957. And cyclic codes can be regarded as ideals in a quotient ring of polynomials mod the polynomial x to the exponent n minus 1. And we denote fq as usual as the finite field with q elements. But cyclic codes also can be regarded as ideals in a group algebra FQCN, where Cn is the cyclic group of order n. Okay, so we conclude that cyclic codes has to do with ideals, and ideals in our case has to do with idempotents. Okay, so our second fact is about constant cyclic codes, and constant cyclic codes were defined by Ewing Berdekamp as a particular case of pseudo-cyclic codes. So our second fact is that constant cyclic codes of length n over fq can be regarded as ideals in a quotient ring of polynomials mod the polynomial x to the exponent n minus lambda, where lambda is in fq star, and fq star we always denote the multiplicative group of units of the field fq. But constant cyclic codes also can be regarded as ideals in a twisted group algebra fq gamma cn, and very soon we will see the definition of twisted group algebra. So the same way as cyclic codes has to do with idempotents in our case, constant cyclic codes also has to do with idempotents, but in a different algebra. And I think in Wednesday, Samir Suena will talk more about this, give more details about this second fact. So other codes such as Hamming codes, alternate codes, Reed-Solomon codes, binary ternary-Golay codes can also be realized as ideals in group algebras or twisted group algebras. Okay, but what is a twisted group algebra? So let G be a finite group and FQ a finite field. Well, so the finiteness of G and FQ is not at all essential for the definition of twisted group algebras, but as we work in with coding theory, we assume that all algebraic structure consider is finite. So we fix, so gamma, a map gamma from G times G to FQ star is called a two cycle of G if this equality holds for all X, Y, and Z in G. And we have some notation as Z2 G FQ star is the set of all two cocycles of G. And we'll further assume that gamma x1 equal gamma 1x equal 1 for all x in G. Okay, let us fix now some gamma, be gamma at supercycle G, and let FQ gamma G this set of formal sums with coefficients AX in FQ. And this is FQ vector space with basis X bar with X in the group G. And this basis is in one-to-one correspondence with the group G. And we can define a multiplication in the vector basis and in basis vectors X as X bar times Y bar equal gamma XY times XY bar. And of course, we can extend this linearly to all elements of the FQ gamma G. So the associated FQ algebra, FQ gamma G, is called a twisted group algebra. So now denote Cn, the cyclic group of order n generated by X, and let lambda in FQ star be, and we can define some cocycle gamma lambda from Cn times Cn to FQ star and define this map as gamma xy xj equal 1 if I plus j is less than n, and we call lambda if I plus j is greater than or equal to n. And this is a two cocycle of Cn, the cyclic group. And it is possible to obtain all twisted group algebras of Cn using these two cocycles, gamma lambda with lambda in FQ star. So let's go back to our main problem to determine the minimal idempotence of the twisted group algebra. So our goal is to extend the following result proved by Molov and Nachev. So these results, I think they prove in 2002. So the statement is, the proposition is, let FQ a field which contains theta 4, where theta 4 is a primitive fourth root of unit. Let C2n be the cyclic group of order 2n generated by X. And let FQ gamma Cn be the twisted group algebra of C2n over FQ, defined by the equality X bar 2n equal lambda in FQ star. So we have a bunch of notation, but the important thing is these two facts. One, H generated by Y is a group of order 2s. And we have that the group algebra FQH is a subalgebra of the twisted group algebra FQ gamma Cn, C2n. And the second fact is the set of minimal idempotence of FQ gamma C2n coincides with the set of minimal idempotence of FQH. Okay, so in order to achieve our goal, we need the following results about polynomials. So this is the second fact. And some results about polynomial. The first result is the following. Let lambda in FQ star with order D, and then the binomial xt minus lambda is reducible in FQX if and only if the integer t greater than or equal to 2 satisfy the following conditions. So the first condition, the greatest common divisor, the GCD of t and q minus 1 over e is equal to 1. Second, each prime factor of t divides e. And the third is that if 4 divides t, then 4 divides q minus 1. Okay, now let f and g be polynomials in FQX, and p of x, another polynomial of degree n, and then we can define the following composition. P f over g is defined by the polynomial g to the exponent n times p fx over gx, and this is again a polynomial in FQX. So we have a theorem. So let f and g in FQX, and p is a polynomial which is reducible of degree n. Then the polynomial p f over x is reducible over FQ if and only if f minus lambda g is reducible over FQn for some root lambda in FQN of Px. So okay, now we have all we need about polynomials. So let us fix some notation. So let D be an integer and theta D a primitive root of units of order D. And for any integer S, we denote by FQ star S, the subgroup of elements AS with A in FQ star is a subgroup of the units of the group FQ star. And we can define for a positive n, positive integer n, and lambda in FQ star, we can define this number h and q lambda equal the maximum of the positive integers s, such that s divides n, and lambda is in FQ star s. So at last, we have the following notation. Let ODI be the multiplicative order of I modulo the positive integer d. Okay, so we are finally ready to state our main result. So theorem, let gamma equal gamma lambda, as we define above, be a Tuchel cycle of Cn for lambda in FQ star. And let H equal H and Q lambda, as we define, and lambda equal BH with B in FQ star. So this is a consequence of the definition of H and Q lambda. And we denote by Y equal to B minus 1 X bar in over H, and big H equal to the group generated by Y. Then for any divisor D of H, we have three facts. So the first condition is that the GCD of N over H and Q to the exponent of DQ minus 1 over D tilde is equal 1. Second condition, each prime factor of N over H divides D tilde. And the third, if 4 divides N over H, then 4 divides Q to the exponent of DQ minus 1, where D tilde is the multiplicative order of B theta D in FQ ODQ star. So, okay, so these three conditions hold if and only if the set of minimal idempotents of the twistor group algebra FQ gamma Cn coincides with the set of minimal idempotents of the group algebra FQH. So we're gonna go through a quick sketch of the proof and we are done. So it is easy to see that H is a cyclic group of order H. So let E be a minimal idempotent in FQH, the group algebra. And by the well-known Perlis-Walker's theorem for group algebras, the idea generated by E in the group algebra FQH is a simple extension of FQ with defining element theta D for some D, so for certain divisor D of H, and with phi of YE equal theta D. And we can take PD, we denote by P dx, the minimal polynomial of YE over FQ. So our claim is that the ideal generated by E in the twistor group algebra is a field. So this means that E is a minimal idempotent. Okay, so let us define psi from the ring of polynomials over FQ to the ideal generated by E in the twistor group algebra. And we define psi by psi of x equal x bar E. And if we take the polynomial f dx equal to PD b minus 1 x n over h, then this polynomial f dx belongs to the kernel of psi, since x bar E is a root of f dx. So we conclude that the ideal generated by E in the twistor group algebra is irreducible if and only if the conditions 1, 2, and 3 hold as desired. Okay, so what can we conclude from this presentation? Idempotent theory is useful in the study of error-correcting codes. In a particular case, we can easily obtain idempotents in a twisted group algebras. So this some reference, and thank you very much for your attention.
Thank you,